Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to three-dimensional figures and cross sections. Before we dive into this, I'm just going to say that please give me a little bit of forgiveness with my drawings. I know that when you guys are working on paper and stuff at home, you probably are not super focused on your drawings, and let's hope the same thing happens here. So when it comes to three-dimensional figures, we have the face of each side, the vertices, and the edges. So I do happen to have my little compact mirror thing here, so it happens to be 3D. It's got a little bit of thickness, not much. So this would be considered a face. That's the flat part. This right here is also considered a face. So the edges are actually like this part right here where two faces come together, if it'll stop being blurry. Okay, so that would be an edge right here along the seam. And then your vertices are your corners. So keep that in mind. And I can show that I actually have a box as well. Let me switch to the box. It's actually my camera box. Okay, so again, this flat part is the face. This is the edge. And this is a vertice. So knowing our different parts is really key to understanding some of these shapes. And we want to make sure we can name them. Okay. So if you were to draw a triangle, and then I kind of usually go back into the right a bit and draw a second triangle that's the exact same shape, and you are going to connect the pieces like that. A little rough. They were supposed, the front and the back were supposed to be the same size. We have drawn a triangular prism. Okay. So the number of faces here, let's think about it. We have the front triangle and the back triangle. Remember, faces are flat sides. And if you think of it like a tent, I don't know if you've ever slept in a tent like that. It's an A-frame tent, it's what it's called. But then you'd have the front door, the back door, then you'd have the left side, the right side, and the bottom. So in our case, there would be 5 faces. When we talk about vertices, we'd have point, 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 point. There's 6 of them. And when we talk about edges, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9. And if it helps you to get like a transparency with that see-through thing and like lay it over your book and count it, then that's great. Go ahead. So remember, the vertices are the corners. Okay. And the edges are where two faces meet. Okay, so the next one that you're probably familiar with is, let's draw a rectangle. And again, I go up and to the right. I don't know why up and to the right, it's just the way I do it. Try to draw the same size. So now I have 2 rectangles drawn. Connect, 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 connect. Now we have a rectangular prism, or a box. All right, and the number of faces, well, we have the front, the back. So front, back, top, bottom, left, and right. We have 6. Okay. Vertices. 1, 2, 3, 4, 5, 6, 7, 8. And edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now we're going to get a little bit tougher. Pentagonal prism. So, have you noticed that I name them by whatever front shape I draw? That's actually the overall base. So this time I've got to draw 2 pentagons and connect it. All right, boom, 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 boom. I'm going to draw my other one in pencil. Might have been a little wide. There's my 2 pentagons. Woo. And then I'm going to connect it. Boy, she did get wonky. Okay. She got really wonky. This is why I don't freehand on my good notes. I will show you my good notes here in a second. Okay. So we have, for faces, we have the front and the back. And then we have the 5 little 1, 2, 3, 4, 5 fillers around the edge, right? So that would be 7 faces. We have the 5 vertices at the front, the 5 at the back, so our vertices are 10. And then we have the 5 blue in the front, the 5 blue in the back, and then 1, 2, 3, 4, 5 orange, so we're at 15, right? Okay, and I'm going to save you from my hexagonal one. Okay, I happen to have these really, really fancy stencils, and look how beautiful these shapes are. Okay, so if you can't draw like me, these stencils are a blessing. So I drew those all with stencils, and you'll notice that all 4 types are prisms, and the whole point behind a prism is that the front and the back are parallel. Okay, so we already talked about the triangular, the rectangular, and the pentagonal. So let's look at this hexagonal. Okay, we have our top and our bottom. There's 2. And then we have 1, 2, 3, 4, 5, 6 panels that kind of go around the outside. So it has 8 faces. Then, if you look at the vertices, we have the 6 at the top and the 6 at the bottom, so we have 12. And then if we look at our edges, we got 6, 6, and then we have the 6 joining it. So that gives us 18. So a couple things that we can notice here. Okay, I've got this all cleaned up right here. What do you notice about, this is a hexagonal, 6 versus 12, 5 versus 10, 4 versus 8. A triangle has 3 sides, right? So 6. So see how the vertices are kind of like your prism type times 2? And if you know your edges, 3 to 9, 4 to 12, 5 to 15, 6 to 18. The edges are 3 times how many ever sides your base shape has. So that's kind of a neat thing to notice as well on a prism. Okay? So, number of sides, your blank prism, whatever this word is, right? If you times it by 2, you'll get your edges, or not your edges, your vertices. But if you times it by 3, you'll get your edges. But there's another relationship going on, okay? So I'm going to write these numbers in order, okay? That way we can see it a little bit more. Kind of that chart. All right. So prism type. We had the triangle, the rectangle, the pentagonal, the hexagonal. we had our faces, our vertices, and our edges. 5. I'm going to put a number over here as well. 5, 6, 7, and 8. Notice the relationship. If you said 2 more each time, you'd be right. Okay, the vertices were 6, 8, 10, and 12. And the edges were 9, 12, 15, and 18. So there's all sorts of relationships and patterns we can find in here, but there's a big person out there, his name is Euler, and he has a formula. He actually does a lot of math. You'll see him in a lot of geometric ideas depending on how far you go. But he said you could take your faces plus your vertices and would equal your edges plus 2. Well, let's try that. Edges plus 2 would be 11, 14, 17, 19, right? Faces plus vertices equals edges plus 2. Okay, 5 plus 6 is 11. Six plus 8 is 14. 7 plus 10 is 17. 8 plus 12 is 20, which happens to be what 18 plus 2 is. I don't know why I said 19. I do. I said 17 plus 2 in my head. Ooh. Got to make sure you stay on top of things sometimes. So Euler's formula definitely holds up, and so it's nice that we can see a relationship between the faces and the vertices, and this is on a prism. Okay, now we found all sorts of relationships just kind of playing around up here. We're going to come back to Euler's formula in a minute. Okay, back to the me not being able to draw thing, right? Let's hope you're a better drawer than I am. My last art class I took was in junior high because it just wasn't my thing. So let's look at pyramids. Now, what's the difference between a prism and a pyramid? Well, prisms have 2 parallel bases, where a prism, or a pyramid, comes to a point. So I drew a triangle for the base, put a single point, right? Or we have our square base. So by the magic of tracing, and because I do not have my stencils here with me tonight, I went ahead and got some rough sketches of a triangular pyramid, a rectangular pyramid, a pentagonal pyramid, and a hexagonal pyramid. So we can see that the bases are still the same, but unlike before, they come to a point, which makes them a pyramid, unlike a parallel face, which made them a prism. So understanding the difference there. So let's go ahead and look at the faces, the vertices, and the edges of these. And of course, we're going to do the triangular, the rectangular, the pentagonal, and the hexagonal. Okay, so let's think about the faces here. We have the bottom, and then we have the side, side, side. So that would be 4 faces. We have 1, 2, 3 vertices, and 1, 2, 3, 4, 5, 6 edges. So a triangle has 3 sides. Right now, we can see all those little observations that we talked about before may not come back in again. Okay, so how many faces? We have the bottom and the 4 uprights, so that's 5. 1, 2, 3, 4, 5 vertices, and edges. 1, 2, 3, 4, 5, 6, 7, 8. Okay. The pentagonal has 1 base plus the 6 uprights, or 5 uprights, for a total of 6. And we have the 5 edges on the bottom, the 5 edges up top. There's 10, and the 5 corners below plus 1, that makes 6. Okay, and the hexagonal has the 6 points plus 1, that's 7. The base plus the 6 sides, that's also 7. And then if you look at the edges, we have this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can see patterns in here as well. We can see that, yes, the faces is just plus 1. Yes, well, it's a little bit harder to see. This should have been 4. Ooh. These were also, like, the faces and the vertices matched. And the edges were double this time instead of triple. But, so that changed things. We couldn't use the same pattern from prisms that we just found. However, does Euler's formula work? Can I get this to equal this plus 2? Well, that would be, they would add 8, 10, 12, and 14. Add 2, we get 8. Add 2, we get 10. Yes, Euler's formula still works. So that's the thing, is that if you do Euler's formula, it works no matter whether it's a pyramid or a prism. So finding all our little patterns, well, that's great and all. But finding one pattern for them all, that's even better. So we can use Euler's formula for all polyhedrons, or 3D shapes if you want to know a simpler word than polyhedron. And that's face plus vertices equals edges plus 2. Okay, so how could I use that? Well, you're going to make a polyhedron with 12 faces and 30 edges. I don't care whether this is a pyramid or a prism. I don't care. I just want to know how many vertices. Okay, that's easy. We're just going to substitute. Faces, 12. Vertices, unknown. Edges, 30. Subtract 12 over. We'd have 20 corners. That's all we cared about there. Do I want to draw the shape? Absolutely not. Now, something else that you'll see talked about, and I'm going to have to rely a little bit on my amazing tracing abilities maybe, is let's say you have something for like a cake. Okay, so picture you have this big old congratulations sheet cake. Oops, I should have stopped. There we go. There we go. Okay. Redo that. Okay, so let's say this is your sheet cake, and you decide that you're going to take your knife and cut it right down the middle. And you're going to split this cake into a couple parts. What kind of shape are you going to see when you cut this cake? Okay, would that be the same shape as if you decided to cut off a corner? You didn't really want the whole piece, the whole depth, and so you just took off a corner. And so that's kind of what we need to think about, is that when we, and I'm going to bring in my better drawings because this is kind of important. Okay, so here we go. We can see that. So cutting it in the middle in separate parts is going to look like a rectangle for sure, right? But what if we had a different shape when we cut it off? Okay, you can think about like a cone. If you cut a cone off the top, like think of your upside down cone, and if you were to cut it, then the top would be a circle. So you kind of actually have to picture, taking something and slicing through it, pulling that piece off, and looking at the shape that results underneath. When we do that, that's what's known as a cross section. So anytime they ask you about a cross section, they're just asking you about a slice. Can you cut it off? Okay. If we cut it in the middle, what's it going to look like? And depending on it, I've got this going ahead. That way you can get it. If I were to take my box and I were to just cut off this section right here, then I would have a funny little like rectangular piece that I have to cover. Okay. If I were to cut it right down the middle, well, then it would just look like two smaller boxes, and the cross section would definitely be a rectangle. I could cut it on a slant, on a bias, right? It might look like a different type of parallelogram. However you cut it. And if this stuff messes with you, here's what I'm going to suggest you do. I'm going to suggest you get Play-Doh. And you make the shapes, and you get a knife, and you cut it. And then remake a shape, and then get a knife, and then cut it. How could you cut it? And that's going to be your best way to practice what cross sections look like. Think about, like, if you make that cut and you were to color in what's left, what would it be? I would say kinetic sand, but kinetic sand kind of falls apart. So yeah, the best way to cut Play-Doh is actually with dental floss. So you can go ahead and cut it with dental floss, and you can kind of make that straight line, that straight cut, to really help you do it. If it's a cone, if you've made it in a cone, you can kind of wrap the dental floss like around the top of the cone, and then just kind of pull the parts and tighten that circle, and it'll pop that cross section off so that you're able to see a cross section much clearer. So that's going to be really a big deal, is playing with Play-Doh if you have trouble visualizing cross sections, which that is something I would have had trouble with whenever I was in high school. I do better with it now, but I still struggle with drawing the shapes. So I, as a teacher, am not going to grade you on the ability to draw, but I will make sure that you guys understand what a cross section is and how if you slice things differently, they will change. The other kind of visualization that's kind of not so bad, but can be hard for some people, is there's those decorations that come to you and they come flat, maybe like this, but what they really are these like party balls or party shapes, to where they're two pieces of cardboard. But if you take them and they're flat right now, and you fold them out all the way until they come back together, they make like this honeycomb kind of thing. So in this case, if we did that with it, and we took this semicircle, and we took this top half and we rotated around, when we got done, we'd have that centerpiece that got rotated around, but we'd now have a sphere. So that's another kind of thing that they do, is they give you a shape, or they give you a cross section, and then they say, hey, rotate this. What would I get? These I'm actually a little bit better at. Okay, so let's say you have a triangle. Now you're picturing a triangle, and you're gonna spin it on this axis, and you're gonna spin it really, really fast. Okay, if you were to keep spinning it really fast, kind of like a wheel going round and round, and you were able to spin, it would start silhouetting a You got what it is yet? A cone. It's going to turn into a cone. So when you take a triangle, especially an isosceles triangle, and you do that, you're going to get a cone. And so you might have to kind of visualize it, get that axis spinning, right? Get the spinner. Maybe it's like maybe you've taken two triangle pieces of paper, you've glued them together, and you put a toothpick in between it, and you spin that toothpick really, really quickly. And if that's what you need to do to start visualizing it, then go for it. But the speedy outline, like even if you like rub the toothpick back and forth between your hands, you would start to see the shadow effect coming in. Okay, and one more. What if I took this rectangle and I were to spin it around this axis? Let's see, this one I think is even easier to see. The reason why I think this one is easier to see is we've kind of done it before. You've kind of taken your notebook and you've kind of spread out all the pages and spread out all the pages and spread out all the pages and kind of made it to where it fluffed all the way out, and this notebook doesn't have enough pages. It works better with a spiral one. But as these pages go back and forth, they're following the path on that edge that is circular, and because we're spinning, right? You get a cylinder. So if you'll notice, anytime I spun something around an axis, I got some kind of circular edge. Sphere, cone, cylinder. And again, any of these things like the cross sections, I suggest Play-Doh and dental floss to help you create the cross sections. With these, if you really need to see it, cut the shape out twice, glue it together around a toothpick, and then kind of picture like roll that toothpick back and forth, right? And you can really see what happens there. So make sure that when it comes to geometry, you're able to actually visualize what's going on so that you don't get lost or stuck whenever your teacher asks you to come up with vocabulary words.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.